In this video we look at graphing exponential functions using transformations, and to do this I'm going to use the same techniques that I did for transformations in my introduction to transformations videos basically. So I'm not going to go over how to do transformations necessarily. I will be doing transformations, but I'll be assuming you have some prior knowledge. So if not, you may want to go find my other transformations videos. Okay, so the first thing we need to do when graphing with transformations is identify a parent function. But let's get an example of a transformed function here, and then we'll try to identify the parent function. And specifically for exponential functions, the variable x is always a power. It's in the exponent. So a parent exponential function is always a number raised to the x power, like 2 to the x, 3 to the x, I don't know, 1/4 to the x, maybe even e to the x, the number e to the x power, some number to the x power. Okay, so let's see an example of a transformed parent function. So here is a transformed parent function that we're supposed to graph using transformations. So the first thing I need to do is identify the parent function. Now in this particular function, the number 2 is being raised to a power. So my parent function is y equals 2 to the x. Notice that the negative is not part of my parent because the negative is not being raised to the power. If it were, I'd have -2 in parentheses like this. But since it's not, it's more like this. It's more like -1 times 2 to the x minus 1 plus 5 is the function we're graphing. And so I have 2 as my base to the power of x will give us our parent function. Everything else here is a transformation. But before we identify the transformations, let's go ahead and get some ordered pairs for our parent function. I already know if I start with an x value of 0, 2 to the 0 power is what y is, because y equals 2 to the x, and x is 0 here, is 1. And then if x is 1, y is 2 to the first, which is 2. If x is 2, y is 2 squared, which is 4. If x is 3, y is 2 cubed, which is 8. Okay, and I could keep going, of course, but let's go the other way. If x is -1, 2 to the -1 is 1/2. If x is -2, I get 1/4. I'm just writing this in the interest of time. -3, I get 1/8. Okay, 2 to the -3 is 1/8. And if we were to graph all these, you can see these y values are getting smaller and smaller, and so we end up having an asymptote, which is the x-axis, or the equation y equals 0. So let's graph our parent function. If you don't understand the asymptote, you'll see it when we graph these points. So 0, 1 is right here. 1, 2 is right here. 2, 4 is up here. 3, 8 is up here. And so the right side of our graph is growing, in fact exponentially, growing very rapidly. If I kept going, you'd have 4, 16, 5, 32, etc. Go to the left, -1, I'm at 1/2. -2, I'm half of that at 1/4. -3, I'm half of that at 1/8. And the graph is getting infinitely close to the x-axis. And so the x-axis is an asymptote. Y equals 0. Now I strongly encourage you to list your asymptote over here with your ordered pairs, because your transformations apply to the entire graph. So apply them to the ordered pairs and the asymptote. Okay, so that's what's new about exponential functions, is you don't just get points to represent it, but you also get this boundary for your graph, your asymptote. Okay, alright, so now let's look at the transformations from this equation. So let's look at the x transformations and then the y transformations. Okay, and I'll go through this quickly since we already know transformations from my other video. For the x transformations, I look at the x part, which for an exponential function is in the exponent. Okay, So the x transformations are what are up here. So I take that x part of the function and treat it like it's in some equation that I'm trying to solve. So x minus 1 equals some number. And then the transformations, the x transformations, are actually the steps it takes to get x by itself. So here I would add 1 to both sides, and that would leave me with x on the left side and some number on the right side. Okay, not the same number, but some number. And so this right here, the plus 1, is what I'm looking for. That's the step it took to get x by itself. So my x transformation is add 1, and since it's an x transformation, I'm just going to add 1 to x. So that's my x transformation. My y transformations are what happens to the parent, the 2 to the power. Okay, so that's multiply by negative 1 and add 5. And those are precisely my y transformations. So multiply by negative 1, so I'll say multiply y by negative 1 and add 5 to y. So those are my y transformations. So I need to apply those three things to these ordered pairs, to this graph, to this asymptote. Okay? So adding 1 to x is what I'll do first. So I'm going to put a plus 1 next to each of these x values. And I'll make my new list of ordered pairs below. So I've got my new ordered pairs here after adding 1 to my x values. And notice that this is a y equation, so I did not add 1. Adding 1 to x does not affect y, so my asymptote stays where it was. So let me draw in the asymptote first, since that's my boundary that I'm approaching. That's right here. And if I plot the points 0, 1 half, 1, 2, or sorry, 1, 1, 2, 2, 3, 4, 4, 8, something like this. So again, the right side of my graph is growing very rapidly, except my graph has been shifted to the right by 1 because I've added 1 to my x values. And then negative 1, 1/4, and negative 2, 1/8. Again, it's still shrinking as I move to the left, getting infinitely close to that asymptote. Now I need to take everything that I've got here and multiply my y's by negative 1. And since this is a y equation, I also need to multiply that by negative 1. It's not going to change the value, but it's still important to understand it still applies to this asymptote. So I'll draw my new ordered pairs, my new asymptote below. So now I've got that here, and I'll graph it. My asymptote did not change. However, since my y values were multiplied by negative 1, my entire graph is going to flip over the x-axis. So I'll draw my asymptote, my boundary first, and then I'll plot the points. And if I plot the points, the right side is now going to grow quickly in the negative direction, and the left side is going to shrink quickly to the asymptote from the bottom now. Okay, so this is very rough, but if you plotted these points, you would see the shape does this. It flipped the previous graph over the x-axis. Okay, let's go see what our last transformation was. Add 5 to y. So I'm going to go to all my y's here and write a plus 5 next to them. And since this is a y equation, I'll put a plus 5 there as well. And now I'll make a new list of ordered pairs and asymptote, and then we'll graph it. Okay, so now you can see we have some fractions here. And you can actually tell that my y values are getting closer and closer to 5, and that's precisely what I see that my asymptote is. When I add 5 to 0, my new asymptote's at y equals 5. So if I were to graph that, I need to label 5 on my y-axis and draw my asymptote there, like this. And now my graph, when I add 5 to my y values, it takes my previous graph and simply moves it up 5 units. So I'm still going to have the same shape, but now it's going to approach this new asymptote, which is up higher, and it's going to look like this. And you would see that if you plotted these points, you would get this sort of shape, decreasing rapidly to the right, approaching 5 very rapidly on the left. And this is the final graph of the transformed function that we began with. So this is the graph of f of x equals negative times 2 to the, what was it, x plus 1? No, x minus 1 plus 5. So we added 1 to x, we multiplied y by negative 1, which meant flipping it over the x-axis. We added 5 to y, which meant shifting it up 5 units. And the key here was tracking that asymptote as we went, because our graph always needs to get close to that. That's a boundary for our graph, and it follows the transformations.